Hello everyone, my name is Joante and my metric number is S6533. Today I'm going to present my FYP1, which is exploring market crash pattern using topological data analysis, as known as TDA. My supervisor is Dr. Pang and my examiner is Madam Sarah. This is the presentation outline. The chapter 1 is introduction, chapter 2 is literature review, chapter 3 is the proposed methodology. I'm going to start my presentation with chapter 1 introduction. Financial markets are trading platforms where buyer and seller exchange their financial assets such as stock, bond, currency, and others. These markets are widely recognized as complex, non-linear, dynamically systems, as they are categorized by highly volatile and strong interdependency influenced by unpredictable factors such as government policy, economic condition, technological development, and unexpected global events. Global events such as Black Monday, dot-com bubble burst, global financial crisis, and COVID-19 market crash in 2020. These major crash events have caused several long-term economic damage across multiple industries. This showed the fragility of financial system and the critical need of early warning signal and system analysis to enable effective risk management and informed decision making. Second part of chapter 1 is problem statement. The first problem statement is inadequacy of traditional economic metric models such as ARIMA and Gantt. The second problem statement is limitation of standard machine learning without TDA. The third problem statement is lack of comprehension phase classification. The aim of this project is to develop a framework that integrates TDA and machine learning to detect and classify stock market phase. By the end of this project, the objectives are to construct a level dataset of market regime, to extract topological features for structural analysis, to develop and evaluate a machine learning model for phase classification. For the scope, we will be using historical data from two sectors, which is airline sector and IT sector. For each sector, we will select 5 stocks with the period of 1,259 trading days. I'm going to begin chapter 2 with theoretical framework. From my left hand side is traditional method without before TDA, and the right hand side is standard machine learning without TDA. Example of traditional method is fundamental analysis, econometric, and technical analysis. This traditional method are good for stable and linear trend and highly interpretable, but they are linear assumption and lacking indicator. The example of standard machine learning is random forest, LSTM, neural network. This type of machine learning have high predictive power and can handle large dataset, but without TDA, they are shape blind and they are only analyze raw number. For their sensitivity, they're prone to overfit noise in volatile market. This is literature review part from the first research paper. They're using casual threshold decision rule and achieve early warning lead time, but they depend mainly on hash node. From the second research paper, they're using a machine learning model called Topological Feature-Based Predictive Model. Their, their result is they validate that specific topological norms are the key for the accuracy to predicting financial collapse, but their predicting power is highly sensitive to the timeliness of training data only. So they are struggling with unknown market event. For the third research paper, they're using Topo Index for their features and visual sliding window analysis for their method. Their result is successfully visualize the distinct geometric shape for bull, bear, and normal face. But in this research, they didn't use the machine learning. The research gap that I can conclude from the previous literature review is lack of ML integration, lack of sector and phase specific analysis, and practical limitation. This is chapter 3, the methodology overview. Phase 1, dataset collection. The historical data is downloaded from investing.com, and I am using 5 airline stock and 5 IT stock in a period of 2 January 2018 until 30 of December 2022. Because this period it have covered the COVID market crash in 2020. So inside the CVS file, we only use the date and closing price, which is price column. This is the line chart of combining the historical data of these 5 airline stock. So you can see in the earlier of 2020, it have a large gap of market crash until 2021. And this is the line chart of IT sector stock price. You can see here in the early 2020 of the COVID period, it only has a small gap compared to airline stock. So here we can know IT stock is more stable than airline stock. Phase 2 is data pre-processing. The data validation is comparing the row count between the 10 historical data of their .cvs file, and also arrange the data in chronological sorting, because when the historical data is downloaded from the investing.com, the that is in descending order. Then the raw price is transformed using the daily log return. Phase 3 is the sliding window segmentation. Using the log return from the previous table, divide it into overlapping window to capture local dynamic and ensure sufficient temporal resolution for earlier warning signal detection of market crash. Each window will be assigned a unique window ID as shown in the table here. And the window size is 84 trading day and overlapping 50% of it. So you can see at the left hand side here, the orange color one is the window one, the green color one is window 2 for overlapping, and the window 3 is the purple color one. Phase 4 is numerical market metric computation. We will calculate the maximum drawdown by using the raw price in the current window. Let's say right now is window 14, and then it will take the highest value inside the window 14 and the lowest value inside the window 14 divided by the highest value in the window 14. For the slope, also the same. Take the price, the end price of the window and the start price of the window divided by the number of trading day. For the volatility, we use log return. For every sliding window I, we compute the standard deviation of daily log return R over the window size W, which is set to 84 days. This is the condition table to show how to labeling the window. So if got previous window label, using this condition to determine next window level. 0 is for normal, 1 is for crash, 2 is for recovery. If it is the first window, it will determine the window level by the entity and slot only. Start from window 2, it will reference to the previous window level and assign the next window level by using this condition table. Here is the table for the window labeling. For the first column is window ID, followed by start date and date of the window, MND, slot, volatility, and label 0, 1, or 2 for the market phase. From the phase 4, we will first put aside the window labeling result. Continue with phase 5 using taken embedding. Taken embedding is to construct the hidden dynamic of the market by transforming the 1D log return series from the very previous stage into a 3D point cloud. M is the embedding dimension. T is the time delay. So this formula is represent how it make a point in the 3D point cloud. The first one, RT, is the X, and then followed by Y, and followed by Z. So it pin a point inside the 3D point cloud using the 3 day of the window, followed by next 3 day, followed by next 3 day until end of the window. In this methodology, we will be using m equal to 3 and tau equal to 1 were selected. Each window is thus transformed into a 3D point cloud represent the short-term trajectory of market dynamic in reconstructed phase space. The 3D point cloud that we construct in phase 5, it will show like in the diagram, left hand side diagram, you will see there are multiple dots on the diagram. That is the point in the 3D point cloud. Undergo the vectorial risk complex, which is VR complex. It defines the shape of the market data by connecting nearby point into loop and cluster. So you can see if the battery risk increasing, the circle surrounded the point will increase also. And then when they intersect, they will have a line connected. It's called connected component. And then using the Reapers library to calculate the birth and death of this feature from our 3D point cloud. Persistent library is to visualize this result as persistent diagram and convert them into a numerical factor. Persistent diagram is shown like the right hand side diagram. The blue one is hash node, and the orange one is hash 1, and the green one is hash 2. For hash node is the connected component, which is a line, and hash 2 is a loop. Loop is like in the left hand side diagram, it got small diagram. The fourth diagram, it become a loop. And then the hash 2 is the void, a space. Phase 7 is the features extraction. Using the Reapers, compute the persistent diagram. It will come out a row list of birth and death time. And using NumPy to calculate the statistical features as shown as the table below. For the diagram lifetime vector, the lifetime is death minus birth, and then we will using this table of features, summary statistic of features in this table, and this one is called TDA features because it's from TDA, and then we will merge together in phase A, merge together with the market metric, which is the MDD, slog, volatility, and the label just now, become a final data set. Coming with the last phase, which is phase 8, supervised learning using random forest. Load the data set that we merged just now, and then separate the features and the label. So X is the features. Features here mean is like the MMD, slot, volatility, and the features from the TDA just now. And the label, the window label is 0 for normal, 1 for crash, 2 for recovery. Separate it, and then split it for 80% to test, 80% to training, 20% to test. We will use random forest with 103 and default depth, and come out with evaluation. The performance is assessed using the confusion metric, precision, recall, and F1 score. Thank you. That is all for me.